In this third chapter, we are going to see some applications of first order equations. And in this first section, we will see orthogonal and oblique trajectories. And the first topic, of course, is orthogonal trajectories. So let's see the definition. And this is the definition. Say this is a one parameter family of curves in the xy plane, where of course you understand that this C is the parameter or arbitrary constant. If you give different values of C, you are going to get different members of this family, which are all curves. A curve that intersects each curve of this family at right angles is called an orthogonal trajectory of this family. That means an orthogonal trajectory of this family is some curve that intersects all the members of this family at right angles, wherever it intersects them. Let's see this example 3.1. Any straight line of this form, which of course passes through the origin and has the form y equal to kx, is an orthogonal trajectory of the family of circles x squared plus y squared equals c squared. Here c is the parameter, which actually is any non-negative real number. This c is the radius of the circle being considered, and these circles all have their centers at the origin. So they are concentric circles all centered at the origin, and any line that passes through the origin of course is perpendicular to all of them wherever it intersects them. It intersects each one of them at 2 points provided that the radius is positive. There of course is one degenerate case which corresponds to c equal to 0. But other than that, all the members of this family intersect this line, or rather the line intersects, same thing actually, all of them at right angles. So this is one orthogonal trajectory of this family. If you draw these things, they would look roughly like this. I say roughly because this is a freehand drawing, so as you can see these are not really circles. But the diagram anyway gives you a rough idea of how things would look. So you can see here 3 members of this family of circles corresponding to different values of C, whatever they are, and all the circles have their centers coinciding with the origin. And say this is one such line which passes through the origin and it meets each circle at right angles. Okay. What angle? The angle between this line and this circle, for example, is by definition the angle between the line and the tangent to the circle at that point. That angle, that is 90 degrees. Okay, so that is why this is an orthogonal trajectory to this family. Looking at the situation from another point of view, if you consider this itself as a family of straight lines where you can vary k, then you would get different straight lines all passing through the origin. For that family, each circle like this would be an orthogonal trajectory. So we can say that each family that you are looking at here, this one has the parameter c and this one has the parameter k. Each family is an orthogonal trajectory of the other family. I mean, we can say that the entire family is orthogonal trajectory in the sense that each member of the family is an orthogonal trajectory to the other family. The problem of finding all the orthogonal trajectories of a given family of curves arises in physical situations also. For example, you have an electric field in 2 dimensions. Then there are field lines which you can think of as a family of curves. Now the equipotential curves, that is curves along which the potential remains the same, they are orthogonal to all the field lines or the flux lines. So they form a family of orthogonal trajectories to the original flux lines. So like that there are many situations where orthogonal trajectories arise. Now here is our main problem. Say you have a family of curves fx, y, c equal to 0. How do you find its orthogonal trajectories? For that, we differentiate both sides of this equation implicitly with respect to x, that we can always do, assuming that y is a differentiable function of x? Well, of course, sometimes y already would be given as a function of x, but sometimes this will just be a relation linking x and y, from which you may not be able to express y as a function of x very easily. But we can always do implicit differentiation, no matter what. And then we would get an equation involving the derivative dy dx, but that equation may have this parameter c. So using that equation and the original equation, we can eliminate c to finally obtain an equation of the following form: dy dx equals some function of x and y. What does it mean? It means that whatever curves this family has, in them actually y is a function of x. And this equation tells us what the slope of such a curve is at the point x comma y, and that slope is given by this right hand side. So if capital C is an orthogonal trajectory of this family, then what? Then capital C would intersect all the curves of this family, all the members of this family at right angles, wherever it intersects them. However, we now know from this equation what the slope of each such member is at any given point. In particular, at those points of intersection also we know what the slope is of each such member. And because C has to intersect any such member at some point at right angles, so the slope of C at any such point would satisfy this other equation. This time, what is dy dx? Dy dx is the slope of C at some given point x comma y. Because of this perpendicular nature, they are intersecting perpendicularly, the slope of C at that point should be the negative reciprocal of this slope, which we already know from analytic geometry. That if there are two, well, by the way, you may get a little confused here. We are talking about curves, whereas this seems to be coming from two straight lines being perpendicular to each other. Well, that is true because ultimately slopes of curves are slopes of tangents at the given points. So straight lines only are involved. This is the slope, this right hand side is the slope of the tangent to any member of this family at the point x comma y. So the slope of the tangent to C at that point where it intersects, say, one of the members, that means at x comma y, would be the negative reciprocal of the slope of that tangent. That is why it looks like this. Now this is a first order differential equation, because from this process we are going to know the right hand side. We would know what the function f is, so we can use that to form this other differential equation. This is one, this is another one. And then solving this differential equation, we would get a one parameter family of solutions. Each solution in that family will be an orthogonal trajectory of this family, will be one candidate for C. This C is arbitrary, so each member of that new family would be an orthogonal trajectory. So that's how we can find orthogonal trajectories. In this next example 3.2, we go back to the family of circles, and this time we are going to follow this procedure to find orthogonal trajectories, and let's see what we find. In the solution, I will just write what's needed for us to understand the situation. Okay, no sentences, nothing. So this is our family. So we straight away do implicit differentiation on both sides with respect to x. The first term gives us 2x, and to differentiate the second term you have to apply the chain rule. You already know these things from calculus. It becomes 2y times dy dx, and the right hand side of course is 0, because although this c is an arbitrary constant, but it's constant nevertheless. So then cancelling 2 from both sides, we get x plus y dy dx equals 0, which if you rearrange, then it takes this form dy dx equals minus x divided by y. So this is that right hand side f of x comma y for this family. This right hand side tells you what the slope of each circle is at the point x comma y. So the equation giving us the slope of an orthogonal trajectory would be this. Dy dx equals the negative reciprocal of this. That means y divided by x. Now we have to solve this first order differential equation, where after rearrangement, it's a simple thing, no? You see that it's a separable equation, which if you solve in the usual way, you now integrate both sides, you get ln y equals ln x plus ln of some arbitrary constant, which say is k, and then getting rid of ln, you get this, y equal to kx. So you see that you are really getting those lines which pass through the origin. And each such line is an orthogonal trajectory of our family of circles. So there you have the procedure. Let's see another one, example 3.3. This time it's a family of parabolas for which we have to find orthogonal trajectories. These are parabolas that have y-axis as their axis and they open upwards. That means they are like this if c is positive, and they open downwards if c is negative. So in the solution, we straight away take the equation of the family and then differentiate both sides implicitly with respect to x. In this case, it's very easy. You just have y as a function of x expressed explicitly already. So you straight away get dy dx on this side, and on the right hand side you get 2cx, but here there is a difference. You still have c, which you did not have in the previous example. So that means using this equation and this equation, you have to eliminate c. From the original equation, you get c equal to y divided by x square. So that way, finally you get this equation where there is no longer c, and the right hand side is 2y divided by x. So the differential equation for an orthogonal trajectory would be this: dy dx equal to the negative reciprocal of this, minus x divided by 2y, from which if you do rearrangement, the equation takes on this form x dx. You can imagine what happened here. X dx plus 2y dy equals 0. Again, this is a separable equation which you can just integrate, and then doing all those things, finally you get this one parameter family of solutions. Each curve in this family is an orthogonal trajectory of the family of parabolas, the original family. And you can clearly see that each such curve is an ellipse. And let me end the video here itself. In the next week, we are going to see oblique trajectories.